Welcome everyone. In this video, we're going to be covering the question of the true number sum. This is a classic algorithmic interview question. There are many different solution routes, each of which involves a different technique. In this question, we're given an array of n distinct integers, meaning that no number in the given array is repeated. And we're also given a number, and it is called target sum, and we need to determine whether there is a pair of elements in the array that sums to exactly the target sum. In this example, we've got the numbers 7, -5, 3, 8, 11, and 6. And we've got the target sum, 9. As I said earlier, we want to find if there is a pair of two numbers here that sum up to 9. So how should we go about this, and how do we go about implementing an algorithm that will traverse this array and somehow find the solution? A naive approach to this problem would be to loop through each number and then loop again through the array looking for a pair that sums to the target sum, in this case 9. The running time to this solution would be O of n squared, because in the worst case we are looping through the array twice to find a pair. So perhaps we can write a faster algorithm that will find pairs that sum up to 9 in linear time. The algorithm makes use of hash tables as we scan over the array and check to see if the target sum minus the current element exists in the hash table. We only need to loop through the array once, and of course this is going to allow us to access the hash table in constant time. So let's have a hash table on the right side here. Okay, we've got our target sum is equal to 9, and whenever we're passing through the array, we've got a current number, and let's call it a current num, which is equal to x. X is whatever number we're at as we traverse the array, and we want to find y, such that x plus y is equal to 9. So this way we can isolate y to be y is equal to 9 minus x, and while traversing the array we have the value 9, which is our target sum. We have the value x, which is whatever number we're currently at, and all we need to do is to apply this formula to solve this equation to find y. And then we say if y is in our hash table, and we can do that in constant time, accessing y in the hash table. If it is in the hash table, then we just return x and y, otherwise we keep traversing the array and we just make sure to store x in the hash table. Okay, let's apply this on the given array and see how this is going to look. We start at the number 7 and we say y is going to be equal to 9 minus 7, and y is going to be equal to 2. Is 2 in our hash table? No, it's not. So we haven't found the two numbers. All we can do now is we can store 7 in our hash table and store 7 to be true, or whatever value you want to store it as. True here means that yes, 7 is present in our hash table. Now we can move on to -5, and we say if we have the number -5, let's solve for y. 9 minus -5 is equal to 14, and is 14 in our hash table? No, it's not. So it seems that we still didn't find our two numbers, and what we need to do now is we need to store -5 in the hash table as true, and we skip this and we move on to the next number, which is 3 in this case, and we solve for y. 9 minus 3 is equal to 6, and we check if 6 is present in our hash table. No, it's not. Okay, then we'll store 3 in the hash table as true. And move on to the next element in the array, in this case 8, and we do the same thing. We solve for y. So 9 minus 8 is equal to 1. And now we check if 1 is in our hash table. No, it's not. Then we store 8 in the hash table. And do the exact same thing to the next element, which is 11, and check if the result of 9 minus 11, which is -2, is present in the hash table, and unfortunately it's not. So we're going to have to store 11 in the hash table. And lastly, we solve for y, and here we say 9 minus 6 is equal to 3, and now we check if 3 is present in our hash table. And luckily it is, and finally we return 3 and 6 as our final answer, as you can see on the screen. Lastly, the time complexity of this solution is O of n, where n is the length of the array. And why is it O of n? Because we only needed to loop through all the elements exactly once. And at each number, we're just calculating y, which is a constant time operation, and then accessing the hash table, which is going to run in constant time. So time complexity is O of n. So, in the other hand, space complexity is also O of n, because we're adding values to the hash table, and since we went all the way to the before last element, and in the worst scenario we could get to the last element, that means that the space complexity is O of n.